Okay, so we've looked at the grain structure of steel. We've looked at, in the last video, what's known as normalizing of steel, which is a heating and cooling process. We're now going to look at hardening of steel, which once again is about heating and cooling. But at this time when we harden steel, we heat it to a higher temperature and we cool it very, very quickly. So we're going to look at what happens in that situation. So we start off with a normal steel structure, which we talked about when we did the grain structure, where we have ferrite, which is soft and ductile, and perlite, which is harder and makes the steel less ductile and stronger and tougher. So that's, as we said too, has a BCC crystal structure, which is body center cubic structure. So we also know that we can only hold up to 0.8% carbon before it becomes all perlite. So we're heating now, but we're going to heat to greater than 1,000 degrees Celsius. And the transformation, as we said, starts to happen at the transformation temperature of about 720 degrees Celsius for steel. And what happens is, just like in the last process in normalizing, we have a transformation from a body-centered cubic to a face-centered cubic type of grain that is called austenite. So in video 1 they talk about another type of crystal forming. They don't tell you what crystal it is. It's actually austenite, which is an FCC, face center cubic structure, and it can hold more carbon than our BCC structure in its interstitial spaces. Okay, so interstitial is something they talk about in the textbook as well. So you know what it is now. It's the gap basically in the structure where we can shove our carbon atoms. So the austenite's forming, and as we go past 1,000 degrees, the austenite grains grow in the grain boundaries, and we end up, once it's past 1,000 degrees, with a crystal that's all austenite. So A equals austenite. So all of these crystals are austenite, FCC crystals that can hold a lot of carbon. So then we start cooling. Now I'm going to do a little intermediate step here. Now what you should be doing if you're going to be hardening is we just quench it, which means rapid cooling, drop it in oil or in water, and a needle-like structure starts to form, which is called, the actual needle-like structure is called martensite. Okay, but let's talk about if we were to just look at what happens when you normally cool it in a slower fashion. Say if we were normalizing, because it's just a little bit more. In the last, when we talked about normalizing, we just said that it goes back to the original grain structure, but this is how that happens. Basically what happens is, in the actual grain boundaries, as the steel starts to cool, the new grains start to form. The new grains are the ferrite grains, which we know about from our original structure up here, ferrite, the softer type of grain. But the thing about ferrite is that it's not very good at, it doesn't have very good solubility when it comes to carbon. I've written here, steel cools, ferrite forms in the boundaries. Carbon has poor solubility in ferrite. So carbon diffuses, which means moves into the austenite. So as these grain boundary ferrite grains form, the carbon that's inside them can't stay there, comes out of solution, and it actually gets sucked into the austenite, because austenite likes, because it's got an FCC crystal structure, it's got more interstitial spaces for carbon, so it sucks up the carbon. Okay, so you can see these arrows are saying carbon, which is what that C represents, is moving from these ferrite grains into the austenite. Now when the carbon in the austenite reaches 0.8%, it turns into perlite. So if we did a slow cool on it, like when we're normalizing, we would end up with these ferrite grains, and then these austenite grains, when they get to 0.8% carbon, would turn into perlite. So we'd have perlite and ferrite just like at the beginning. And when we normalized, and if we did it at the speed that we used for normalization, the grains would be smaller. Okay, so we didn't mention that in our normalizing discussion because we didn't want to make it over complex, but we really need to talk about this process of diffusion of carbon, not to make it overly complicated, because I actually want to tell you why we end up with martensite. Okay, so instead of doing a slower cool and allowing this diffusion to happen, because diffusion of the carbon from one place to another takes time, but what happens when we heat it up really hard and we just cool it really quickly is the carbon doesn't have time to diffuse, so it doesn't have time to become pearlite. So what ends up happening is, I like to use the analogy of making a cake. If you're in Master Chef and you've got plenty of time to bake the cake's going to look really nice. But if someone says to you when you're like 3/4 of the way through the cake, or you haven't even started, you've got 5 seconds to bake this cake, the cake's going to be a huge mess. And that's what happens to the crystals. So the carbon doesn't have time to diffuse into the austenite when you quench it, when you just drop it from 1,000 degrees straight into the water. So it doesn't have time for this process here where the ferrite forms and the carbon, because it's not soluble in ferrite, jumps into the austenite, and then the austenite becomes pearlite. That diffusion takes time. So there's no time. So what ends up happening is these needle-like, highly stressed crystals that are interspersed through the BCC crystal structure form. And these crystals, which they talk about in the video, in video number 1, and I've got a video number 1 reference here of 14 minutes and 58 seconds when they're talking about hardening, these needle-like structures are highly stressed, and they create a very brittle type of steel. Very hard, but very brittle, and it's called martensite steel. So, you might have a reason to want to have a very hard steel because, for instance, if you're making a knife, you don't want the steel to be ductile, you don't want it to bend, and you want the actual blade to keep its edge and remain sharp. But the only trouble with this type of steel, if you made a knife out of it, is that it would be very sharp, but it would also break very easily or snap very easily. So if it was a meat cleaver and you were cutting a piece of meat and it hit a bone, it could chip the blade or snap the blade. So what do we do about that situation? We use a thing called tempering. So tempering is something we do to harden steel to make it tougher so that it's not going to break. It's not going to be as brittle. So that's what we'll talk about in the next video when we get to it. See you in the next video.